Friends, I have finished 38 lectures on the subject of extraction of non-ferrous metals. And then I invited a good friend of mine, Mr. Pugajendi, who has delivered two very beautiful lectures. I had specially requested him to talk about the importance of non-ferrous metallurgy as regards the economy of India today, how there is a resurgence in the non-ferrous industry, how it can be an attractive option from our metallurgy graduates. And you will appreciate how beautifully he has presented the subject. He holds a very important position and he is very well thought of in the non-ferrous metals academia as well as the industry circle. Fortunately, he has repeated far more effectively some of the things I had mentioned about our history and how things are changing. I would not go into that. In the next two lectures, what I propose to do is to go through the entire set of lectures that I have delivered and remind you of some important points. Now, I have mentioned and I will mention it again that you always understand principles better once you know what actual processes there are, and you understand processes better when you know the principles. They go hand in hand. So, we started the lectures with discussion of fundamental principles, then we talked about processes, trying to point out how the principles apply, but I am sure you begin to understand the importance of the principles only when we discussed the processes. Now that you have understood some of the principles and you have become familiar with the processes, the techniques and some details, I can now have a different kind of discussion putting them together. So, I will do that for next two lectures, 41 and 42nd lecture. You would recall that I had started my lectures by saying how non-ferrous extractive metallurgy is a bit different from the other undergraduate metallurgy subjects. Some people think of it as more of very descriptive, not very analytical, not very quantitative. I hope that I have been able to show, at least to some extent, that non-ferrous extractive metallurgy is really not that dull a subject. There is a lot of logic, there is a lot of beauty in the things that are done. It is true that there is a lot of chemistry, more of chemistry than of physics, not that much of mathematics, but certainly there is rationality and some quantification, quantitative principles. I started by mentioning two equations, one on reduction of titanium tetrachloride by magnesium and sodium, and another was on aluminothermic reduction. Now, so far as this reaction is concerned, in course of chemistry we will write these two equations and that is the end of the matter. But I mentioned in my lectures that for a metallurgist it becomes a starting point for asking questions as to how do these reactions actually take place. Their mechanisms are different, and subsequently I have discussed and shown that the magnesium reduction often produces a different kind of product, a powdery titanium, because it is a molecular reaction, whereas the sodium reaction produces a crystalline product because it is electrochemical in nature. So, the reaction mechanism is very important. In the second reaction, there was another reaction that's yes, I explained why the sodium reaction is electrochemical, because there is subhalides in the sodium chloride phase which can be detected, and much of the reaction takes place because of the sodium vapors reacting with subhalides in sodium chloride phase, and not sodium vapor and titanium tetrachloride molecules in a gas phase. That reaction is not very probable, and that was the basis of explaining how things happen at all. And then I said, if there is a metallic conductor, then it is conducive to electrochemical reaction. That is why you must have a metallic chamber. The other reaction was aluminothermic reduction of metal oxide. Such a reaction is exothermic, produces a lot of heat. So, in a chemistry course, one may learn that this reaction is very favorable from energy point of view, because it is exothermic and it is autogenous actually. Once you set it off, it does not need any external heat supply. But later on in the course, we have learnt that you have to analyze energy requirements by looking at things in a holistic manner. If you take into account the energy that is required to produce aluminum to start with, then this reaction is not necessarily favorable from energy point of view. It may generate some heat, all right. It may not need much of an external heat supply, but it has the raw material has consumed energy in the first place, and if you take that into account, by taking that account you have to calculate process fuel equivalent PFE, and unless that is favorable, you cannot call this favorable. As a matter of fact, it is really not favorable, because aluminum needs enormous amount of energy in its production. So, in our non-ferrous metallurgy course, we will look at reactions from a different angle in terms of mechanism and in terms of thermodynamics, in terms of kinetics, and that is what I moved into subsequently. I did show you this poem that says that iron is master of them all, but then non-ferrous metals are not necessarily poor cousins of steel. They have their uses, and some uses are absolutely strategic and critical. You cannot think of modern age without aluminum alloys, titanium alloys, which go for aerospace applications. You cannot think of copper, which go in for electrical applications. You cannot think of the electronic industry without silicon, and there are many non-ferrous metals which are vitally required for various applications. So, we can call steel master of the iron master of them all, but the others are really not that inferior. Then I had given you some figures, and Mr. Pugachendi has given some more figures which are perhaps more correct and more up to date. The idea was to show that the non-ferrous metals industry in our country is expanding, but even then we are far behind the international scenario, particularly if you look at aluminum, which is so very important for India's economy, that industry has to expand in a big way, and all metallurgy graduates will have a very important role to play if we want to sustain the growth and expansion of our non-ferrous metals industry. Now, having said that, I went back into the history, because in our learning objectives it was there to discuss past also. And so, what we did, we discussed very briefly about the history of non-ferrous metal production in India, and I mentioned that our history was something very enviable. In ancient world, 7 or 8 metals were known, and from ancient times India was producing them. But India had something which no other nation had until very recent times. It was zinc. India learned to produce zinc very early, by 4th or 5th century AD, and the industry came to almost a peak by 11th and 12th century, until after the Muslim invasion things began to decline. There is a reason why Indians are so crazy about zinc, because zinc went in for making brass, which was almost a substitute for gold. Indians have always been crazy about gold. So, there were alchemists like Nagarjuna, who was trying to make gold, and very often the brass they made was just as good as gold. And when kings and emperors ran out of gold to cover their temples and monuments, they fell back on brass. Brass was, and also for the ordinary public who couldn't afford gold, brass was good because it also shined shone like gold. Now, after having discussed the history and we showed some very good nice pictures also, I have referred to these couple of books which I recommend you read sometime, maybe after your graduation, to know about the minerals and metals in ancient India. There are 2 volumes. One volume is on archaeological evidence, the other is on literary evidence. For all our texts, we know about what was there, to what extent they were there. There is another book on minerals and metals in pre-modern India, just when the Britishers came. That also gives us a lot of things about what was happening in the area of non-ferrous metals. And then we went through some, I will go through them quickly, over the development of the metals by mankind over the millennia. Actually, things began to happen in Egypt, Mesopotamia, then Indus Valley, and then China also started. Many of them started independently, or they have been exchange of information. But we know that around 2500 BC, there was onset of Chalcolithic age, which meant copper and stone. People were beginning to come from Stone Age to use of copper, and first came bronze, because tin has a lower melting point and bronze had beautiful properties. And very often we say Ayas, that is referred to in Vedas, it is not necessarily iron. Ayas could mean bronze also. People became familiar with gold, copper, silver, lead, tin, mercury, iron, antimony also. Then how copper and iron came, they may have been kind of accidental. There are many conjectures, I have talked about them. The point to note is that zinc came into the picture as a metal much later, and India was the first country to learn this around 400 AD. West learnt the technique only in the 18th century, because the Indian producers have kept their technique hidden from the rest of the world. Only from the end of 18th century, many newer metals were beginning to be discovered. Before that, there were only a handful of metals, and strangely aluminum could not be produced. It was produced in small quantities by chemistry, but it could be produced in bulk, because 3 things happened together. We had the invention of electricity. Electricity could be used for electrolysis, and a process was invented simultaneously in America and France. They are called Hall-Héroult process, which was possible because there was electricity, but it was also made possible because huge quantities of pure alumina could be produced by Bayes process. If Bayes process was not there, it would not be possible to produce aluminum in bulk, because you cannot electrolyze bauxite as it is. You have to purify, you have to produce pure alumina. For that you need Bayes process. So, in technology, many advancements have taken place, because 2-3 things have happened simultaneously, and they have helped each other. Aluminum is an example. I have talked in detail about the literary evidence in our ancient texts, starting from Rig Veda, mention of various metals and alloys. I have talked about archaeological evidences from numerous excavations which have yielded thousands of artifacts of all kinds of metals and alloys. Not only sculpture, but tools, weapons, personal ornaments, objects of domestic use, everything, figurines, they are distributed all over India. There is a large concentration in western India, but then things spread to the south, down to the east. So, there were numerous sites in India where these things were produced. Here is a story as to how the ancients learned to iron production. Then this is one of the oldest examples of a non-ferrous metal figurine in India, the dancing girl of Mohenjo-daro. It is a small sculpture with very interesting features, bangles only in the left arm. Unfortunately, this is Mohenjo-daro is no longer in India, it is in Pakistan now. But then from the submerged Dwarka of the coast of Gujarat, lots of objects have been found which were made of copper, zinc, lead and all kinds of alloys. And here is a picture showing where archaeological sites have been found that have yielded many non-ferrous metal objects. I showed you pictures of some ancient copper making furnaces, also distillation units for zinc. Many of them are still intact in the hillsides in Rajasthan, because it almost looks like when the distillation units were all charged and ready for production, maybe they were flooded, and those who were to operate them, they left the area, they are found intact. On the hillsides you find these retorts. Indians used both horizontal retorts as well as vertical retorts. Mr. Pugezendi is showing some pictures. Then I showed some beautiful sculptures starting from as early as 7th or 8th century. They were brasses, bronzes, and they are astounding not only because of the quality of the alloy that was produced in India, but also the beauty and the aesthetics, the craftsmanship, the high skill of the artisans. And one of the techniques they mastered was the lost wax process, where actually things that were made, they were really not solid, they are all very hollow. So, there is a thin layer of metal which make these things. The famous Nataraja, which its beauty has an international impact, and so many books have written on it. There is a book called the Tao of Physics, where there is a big chapter on this Nataraja concept, what all symbols are there, what all it means, and the author has thinks that is one of the most beautiful things. This is Ardhanarishwara. There is also another sculpture. Then in recent time, pre-modern times, when the Mughals were declining, they made this beautiful birti ware. There was another special kind of alloy and special kind of craftsmanship. So, I have discussed all this. This was the first module, which was kind of introductory to the course. Then I came to the second module, which was little more on the dull side, bit descriptive, but it had to be done. It was the learning objectives were sources of non-ferrous metals, land and sea, principles of exploration, principles of ore beneficiation, and something about the non-ferrous metal wealth. The point to note in this was that metals do not come from land alone. There are metals in the sea also, and I have given you some data on their distribution. So far as the land is concerned, we can extract metals only from the surface of earth. The surface includes sea also. When we say crust of the earth, it is about a few kilometers is what we can normally take samples out from. So, the average things percentages have been shown, and that I have discussed at the end of the lectures also, that we have shown that oxygen, silicon, aluminum, these are there in plenty, and that is why you find oxides, silicates. There is also calcium is also there. Some of the other metals we are very familiar with, like base metals, copper, lead, zinc, their abundance is very low. So, had they been distributed uniformly all over the crust, it will be very difficult to extract them. Fortunately, there are pockets where they are concentrated. That what helps us to get them, extract them. So, we have discussed the nature of occurrence, that different metals, because of their difference in reactivities, occur in different forms. In some form they are more stable, some minerals are more stable, they are difficult to decompose, some other minerals are not so stable. I have given you some tables about that. And then I have said that an extraction process will have to take into account the percentage of impurities, their association, physical conditioning of the ore, location and magnitude, proximity to transport facilities, market value of the metal if at all extracted, then value of land, cost of rehabilitation, environmental, social concerns, all these to set up a non-ferrous metal industry. So, many factors go into the production of non-ferrous metals. It starts with exploration that are based on magnetic studies on land, studies on electrical resistivity. These things tell us where water bodies are there. Some such things can be done from air also. Aeroplanes fly according to some grids, and electrical flow lines or equipotential lines are drawn, which indicate where water, where ore bodies may be there, and then detailed explorations are done where actual samples are taken out, the samples analyzed. Doing all this, only people go for exploration. Now, if we take the world average, the average composition of the crust, this is the list of abundance. The elements on top are oxygen, silicon, aluminum, iron, calcium, and then there is after magnesium there is a drastic drop, and I have said a few elements account for more than 95% of the abundance. But still we managed to get many elements which are, the average shows very low figures, but fortunately they are found concentrated in certain areas. That is why we were able to extract them. Interestingly, we should remember that sea also contains all elements, because over the millennia rivers have washed down things all from all corners of the earth's surface and dissolve them. Elements come from the bottom of the sea also, through undersea cracks or volcanoes through which things are constantly coming out. On an average, these are the relative abundance. Of course, chlorine is maximum, that is why you have chloride salts. You have sodium and magnesium, these are sodium chloride and magnesium chloride. There is also other things, sulfur, calcium, whole lot of things. And if you go down, you can find there also precious metals are also there, like you have gold, silver, all that is there. But then because the percentage is so small, even uranium is there, it is not easy to extract those things from seawater. Fortunately, there is some concentrated source of things in the sea in the form of manganese nodules, solid nodules which are continuously forming and getting distributed in sea floors, not in a uniform manner. Some sea floors have more, some have less. They are very rich in manganese, because the highest concentration is, we call them manganese nodules. It might look like a very good source of manganese, but unfortunately on land also we have very rich manganese very manganese is available on land. But it is more attractive from the point of view of cobalt, zinc, which compared to what is available on land is very attractive, and people are interested in extracting cobalt, zinc, nickel, etc., from those manganese nodules. But then extracting manganese nodules from the bottom of the sea, which could be several kilometers down, is not an easy proposition. There are fortunately some shallow seas which also have these manganese nodules. So, extraction has to start from there. India is very much in this game. In National Metallurgical Laboratory, Hindustan Zinc Limited, which is now Sterlite, in Regional Research Laboratory, which is now called Institute of Minerals and Materials Technology, a program has been going on for 20 years, and it has gone to a pilot plant scale. But it is basically for the future, that if you really have to get cobalt, zinc, nickel, we can get from the manganese nodules, but the process would become better, more economical when we extract also manganese and iron, which are in good quantities. Then the total on the whole, the economics will be better. We have talked about worldwide distribution of important metals, which country is richer in which. The God has not been kind to every country in the same manner. Some countries are very rich in mineral deposits. America, South Africa, parts of Soviet Union, Australia, very rich in mineral wealth. India is rich in some, but not rich in some others. We would have liked it to. For example, the mineral wealth of India is adequate to abundant so far as ores of aluminum, beryllium, chromium, manganese, magnesium, titanium, zirconium, thorium and the rare earths are concerned. We say that we have inadequate, but we have some definitely ores of copper, gold. I have put graphite here also because it is an important thing, though it is not a metal. Lead, vanadium, zinc, cadmium, nickel, uranium, tin we have. But 2 or 2 not known so far are they also include many metals: antimony, bismuth, boron, cobalt, mercury, molybdenum, etc., silver, tungsten. They are not there. So, Indian metal industry, non-ferrous metal industry has to depend a great deal on where we have adequate or abundant resources. It does not mean we should ignore the others, because if we have the skill, if we have the knowledge, we can always import concentrates from elsewhere and process them and produce add value. You can get concentrates of those metals which are available in other countries, and if they are willing to sell, we can add value, extract those metals. Then we went into the subject of mineral beneficiation, which very often starts with crushing and grinding. There are some pictures of grinders. Say this grinding always has the ore particles go through a gap where we have the grinding surfaces rotating to force the particles to go through, and that is when size reduction takes place. There are different kinds of mills. These are self-explanatory, but towards the end of my lectures I mentioned these days the subject of crushing and grinding is becoming very important, because it is extremely energy consuming step in the entire process of mineral beneficiation. We saw that in copper extraction processes 75% of the energy is going into the very first step of crushing and grinding to produce a fine ore from which through flotation will get a copper concentrate. So, there is now tremendous urge to develop newer kind of crushers and grinders, and we have talked about high pressure grinding mills, where suppose this is the kind of grinder, these two rolls will be pressing from two directions as the particles go through, they are not fixed. So, these high pressure grinding mills are more efficient, they save on energy. This is regarding how particles fracture, they can fracture along the grains, they can fracture across the grains. Then I have talked about what kind of particle size that different particles have. Then we have come to various methods of concentration, and there the central thing to remember is different minerals have different kinds of properties. Magnetic susceptibility of one mineral is different from the other, electrical susceptibility, their density, size, shape, they are different. So, these properties will be exploited. An electrostatic separator exploits electrical conduction properties. Like if we have a rotating drum that attracts particles, which are most attracted, that fraction will go here. No, the other way, the electrically conducting particles will go there, non-conducting particles will go there. So, these are the kind of properties we exploit, brittleness, just by crushing and grinding we can separate fractions, size difference, size and density, magnetic permeability, susceptibility, conductivity, surface properties, in flotation surface properties are done. I have given you one interesting example which is used in processing of beach sands, which have come again and again when we talked about monazite concentrate, we have talked about ilmenite processing of beach sands in general. And because it is such an important area, processing of beach sands, I took in the beginning only one concentration device, that was spiral concentrate, which is used for beach sands, which has many minerals, very heavy minerals, ilmenite, rutile, zircon, monazite, heavy minerals like garnet and sillimanite, lighter minerals like silica. We need to fractionate, we need to separate all this, and then they will go for their different circuits. And how does it function? We have shown you a picture. A slurry will come down from the top, it will come at increasing velocity, rotating, and during the process of rotation, the particles, minerals will get separated depending on their density and shape. And we have explained how this happens, that in the perimeter outermost mostly water with fine particles will go, that can be collected separately. That is where just out inside the perimeter the velocity will be highest, and there cannot be not much separation. Maximum separation will be inner regions, which is where the velocity drops and begins to slow down, and heavier minerals separate there. Then I have said the whole thing is really not very descriptive. We can now put in mathematical models, we can bring in computer applications, we can do optimization, we can consider a particular, say a fraction, heavy metal concentrate, and we can do experiments and use design of experiment to set up empirical equations from which we can optimize things to find what are the best conditions of getting one fraction out in quantity or quality. Something that the industry traditionally used to do by lot of trial and error over years, now today can be done in a matter of days using computer packages. And then we have done this in Indian rare earths, and we have made lot of predictions, plotted this sort of response surfaces using standard computer packages to show under which conditions you get maximum concentrate, etc., and they have been found useful in the industry. Then we move to module 3, which was principles of extraction and refining processes, and that was a fairly long thing. Now, in many universities there can be a full 1 semester course only on extraction processes. There can be a course only on principles of refining. Now, I have quizzed all that into a few lectures, taking something from here, something from there, and these lectures can never be a substitute for your learning by really going and reading various books which are available. Now, in the days of internet, on any subject you can get so much of information. So, essentially if you have at least some idea as to what is what, you can always go to a source where you will get lot more details when you need it. Now, in this module our learning objectives was to understand why some metals exist in nature as stable complex minerals and some do not. We wanted to understand some thermodynamic and kinetic principles of heterogeneous reactions, because in metallurgy most reactions are heterogeneous. Heterogeneous means either solids liquiding with gases or gases and solids in contact or solids and liquids in contact. Very rarely we had an example of something happening in a homogeneous gas phase or a homogeneous liquid phase. So, we always talked about heterogeneous reactions where more than one phase is involved. Then we went to understand principles of pyrometallurgy, electrometallurgy and hydrometallurgy. This was where I showed a periodic table to tell you where we find metals, non-ferrous metals. I told you that there are so many non-ferrous metals, about 80 of them, because all are non-ferrous metals if you leave aside iron, the halogens and some elements which are solids, but they are not metals, because metals are supposed to have some properties like luster, some strength, but then there are some exceptions. Graphite has luster, but it is not a metal. Mercury is not a solid, it has a luster, but it is a metal. Why we call them a metal? Because metals are supposed to have some reactivities, and to show that I showed you a table where metals have been listed in terms of their reactivities. Now, what is the criterion of reactivity? There are many criteria. I have listed here electrode potentials, apparent standard potential, standard formation potential of pure chlorides, free energy formations of oxides and chlorides, electronegativity. I have not gone far too deep in the subject, but I should mention this. There are different fundamental principles behind all such listing. The list we get using different criteria do not give identical listing, means which is on top here may not be on top there, but then by and large you will find some metals are coming to the top, means they are very reactive. They are very reactive towards halogens, oxygen and things like that. Like cesium, potassium, beryllium, sodium, lithium, calcium, you will find them all at the top everywhere. Whereas, some metals like platinum, gold, silver, etc., they will all be at the bottom. They are not at all reactive. Metals like copper also would be towards the bottom. Things like lead, tin, iron, zinc, manganese, they will be somewhat at the in the middle. By electronegativity we mean these are electropositive metals, going down is electronegative. Those which are electropositive will have greater negative values of free energies of formation of either oxides or chlorides, means they make very stable compounds, and when they are stable compounds, it will be very difficult to dissociate and get the metal. Same in terms of electrode potential. Electrode potentials are with reference to hydrogen as 1. Now, electrode potential tells us there is a line we can draw at hydrogen with reference to hydrogen taken as 0. All below elements below that, metal below that are electronegative, all above that are electropositive, which means these metals should not normally be obtained from aqueous media by electrolysis, because if that comes, it will immediately react with water and liberate hydrogen. Like if you have somehow get magnesium out of water, it will not be magnesium, it will react with water, immediately liberate hydrogen. Normally that would happen for zinc also. Zinc in an acid medium will liberate hydrogen. But when we pass a current, there are some phenomena, and that we have discussed, called activation over potential, which changes these electrode potentials because of certain reasons, which I will discuss a little later. And that is why under the conditions on passing of current, this listing changes and hydrogen will come on top of zinc, and sometimes it can be done from manganese also. Means up to manganese, all metals below that can be produced by electrolysis of aqueous solutions, acid solutions. These, the ones above, cannot be. So, this gives us an idea as to what this listing is all about. If you go a little further, these reactivities will also tell us how they should exist in nature. Those which are up here will form very stable oxides, silicates, aluminates, halides in nature, very stable compounds. At the bottom, when we have platinum group metals, gold, silver, etc., their reactivity is very low, they will not form compounds, they can exist in free state. The ones which are near the bottom, like lead, tin, nickel, etc., will form compounds, but very weak compounds. They are very easy to dissociate, no problem at all. Little bit of reducing atmosphere will reduce them. So, we made a category of metals, we put them into 4 categories depending on electrode potential. Those which were very high, we said they form chlorides, carbonates, sulfates, etc., very stable compounds. Then gradually they also had other property, those which are very stable compounds, they will spontaneously react with water, they will form ionic compounds. Those below will form also stable compounds, but they will not oxidize unless we heat them. They will not oxidize spontaneously in air, like sodium, if you take it out in air, it will oxidize. But these metals, which are slightly less reactive, will get oxidized only heat, and they will be attacked by steam. They will not be attacked by water, because their reactivity is slightly less. If you go further down, they will form simple or complex oxides or sulfides. They will oxidize only if there is a strong heating or there is a strong oxidizing agent. Ores are easily reduced. Below that, we are coming to elements which form weak compounds. They will form selenides, tellurides, arsenides, which are very easy to reduce, and of course, which will decompose at high temperatures only by heating. Such metals will not be attacked by steam. In many cases, it will show complex bonding in compounds. and then at the bottom we have elements, many of them will occur in free state or will occur as weak sulfide tellurides, etc., etc. Many will not be attacked by acids at all, unless it is a very special kind of acid like aqua regia and things like that. So, as the reactivities go down, the nature of compounds also become different, weaker compounds here, stronger compounds on top. Accordingly, our extraction processes also change. Then we started with pyrometallurgy, which was the ancient method, because when humans, when first invented fire, they experimented a great deal with fire, starting with cooking of food, roasting of animals. Then they saw the effect of fire on mud. Mud became clay when it was heated to a certain temperature. The clay was much stronger, it did not dissolve in water. So, clay pots could be made into pots which are very stable. Then they found accidentally some metals elements, some minerals decompose, like if there was mercury sulfide, it decomposes, produce mercury. Then accidentally or by design or by trial and error, they learned to apply pyrometallurgy in the production of bronze, in the production of lead, in the production of iron, in the production of various alloys. Advantages of pyrometallurgy is that compounds become less stable at high temperatures. So, even if you have stable compounds, compounds become unstable. So, you have to bring in a reducing agent, the element will get separated from whatever it is combined with. Reaction rates will be high, because in kinetics temperature is high, reaction rates are high. Then at high temperature some reduction reactions become feasible, which cannot be done at room temperature, can be done at high temperature, and there is a greater ease of separation of metal and slag. So, clean liquid metal can be separated out. Now, there are many steps in any roasting operation. Oxidizing, first is roasting, you roast, and in roasting there is necessarily release or some gaseous substance. Oxidizing roasting means you change, say, carbonate into an oxide. Volatilizing roasting means you take out some volatiles. Chloridizing roasting means you make a chloride. Reduction roasting means you reduce. There are different kinds of reduction techniques in pyrometallurgy. One can reduce by carbon, one can reduce by metals, one can reduce simply by heating. There are some reactions that a reducing agent reacting with a compound will release the reducing agent. Sometimes the metal that comes out is gas, sometimes it can be solid or liquid. Sometimes what you form by the combination of the reducing agent and what was there with the metal, that can be gas, that can be solid, there are all kinds of combinations. Thermal dissociation, as I said, mercury sulfide. Sometimes simply by heating we can recover the metal, and that sometimes vacuum has a role to play in all this. If there is a gaseous substance on the right, vacuum would drive the reaction to the right. If there is a gaseous substance on the left hand side, reaction can be driven by use of pressure. I gave you referred to some books that you might find useful. There are many other books. Then we came to a very important subject. This is a basis of pyrometallurgy. The standard free energy diagram for oxides, also known as Ellingham diagrams, which plot free energies of formation against temperature. And these plots are always with reference to one molecule of oxygen, because that helps us in our, when we associate two reactions, we can add or divide we can subtract one from the other, and very easily one HO2 and one O2 would get cancelled out. Now, in this plot, the thing to note is, for all oxides, all metal oxides, the plot goes upward, which means the free energy of formation becomes less negative with temperature, all metals. And that becoming less negative means they are becoming less stable. On the other hand, when carbon reacts to form CO2, the free energy of formation hardly changes with temperature, but when we consider formation of CO, we find it has a negative slope. These have a positive slope. The line for CO2 has 0 slope, line for CO has negative slope. The slope is related to change in entropy. All these have a reaction indicating metal with one molecule of oxygen forming the oxide, and all these reactions imply disappearance of one molecule of oxygen, and that is what gives a change in entropy. It is the same for all. In the case of C plus O2 giving CO2, same amount of gas on the left hand side, same number of moles on the right hand side, slope is 0. Here it is the other way around. You will find C 2C plus O2 is 2CO. So, when one mole of molecule of oxygen disappears, 2 molecules of CO are produced. So, we have a negative slope, and this is of great importance in pyrometallurgy. It shows that this line crosses all the lines for the oxides. So, there is always a point where carbon monoxide becomes more stable compared to the line for the metal oxide, and when that happens, carbon can reduce the oxide to form, release the metal and form carbon monoxide. Now, for metals which are more stable like aluminum, zirconium, etc., the crossing point is at a much higher temperature. You have to go to much higher temperature. Whereas, when the metals are not so stable, the oxides are not so stable, they can be reduced by carbon to form when it forms CO at a much lower temperature. So, essentially everything can be reduced by carbon, but there is a problem. Oxides which are very stable and according to Ellingham's diagram can be reduced at very high temperature also form stable carbides. So, very often carbon reduction will not be applicable to them. We have to find something else to do it. Say if we have BeO which is very stable, you will find the line for BeO is fairly low down. BeO plus carbon, if we do, will produce beryllium with carbide, but we do the reaction in presence of copper. So, we produce a beryllium copper alloy where the beryllium activity is very low. Having copper drives the reaction not to the right, no, having the copper produces beryllium copper, activity of beryllium is low, therefore, the reaction is driven to the right. Activity is low means it will not form a carbide. Another advantage is here, in the industry you want beryllium carbide, but it is not applicable in all cases. We like to avoid carbide formation. I will stop here now and proceed further, because I would like to review the entire course very quickly. Thank you very much.